Good morning, everyone. My name, as you know, is Mark Fennell. I'm an author, teacher, scientist, bunch of eclectic things. Today, I'd like to talk to you about the three different ways that most physicists will look at the universe or will look at a phenomenon. There's physical, mathematical, and geometrical. Physical, mathematical, and geometrical. I prefer the physical. I think it's the best way to look at the world to describe what it is. You can describe a sofa. You can describe a dog. You can describe a chair. It's an object you can see in front of you. I can tell you the colors, the textures. I can tell you how it operates. That's physical. That's what I prefer to do. But alas, the vast majority of scientists do not. Most scientists prefer to go mathematical, and they will describe the chair or the sofa with particular mathematical equations. And then, of course, there's the geometrical, which they're going to describe the phenomenon with measurements and geometry, height, width, length, and those sorts of things. I would say 99% of physicists go for the mathematical. And when you ask them any questions, it will all be these lists of mathematical equations. You can see from this equation, I can't see anything. So, what is motion? Oh, here's the equations. What is gravity? Here's the equations. That really doesn't help me. I want to know what it is physically. Then there's geometrical. Geometrical is more useful than mathematical because at least you're getting a shape. You're getting a structure. At least we're getting close. But it's still not quite as good as physical. Here's one example I like to use. A bicycle tire. I can tell you about a bicycle tire. You already know what one looks like. You've seen them. So you automatically have that visual in your head. Even if you didn't, I could describe it as a wheel, a circle, made of rubber and filled with air. So you see, I've given you a geometry, a wheel, a circle. I've given you material, rubber, and filled with air. And then I can proceed to tell you the motions about how we, push on the tire, and that will cause the energies inside the air molecules to move it forward, and so on. Okay, so we can describe it in that way. The geometric physicist would say that bicycle tire. So what is a bicycle tire? They say it's a circle. It's a circle. It's a circle. It is a circle, but a lot of other things are circles too. And, it really doesn't, it only gets you so far in your understanding. But then what comes, I think, is the worst is the mathematical, which again is 99% of the physicists out there. You say, what is a bicycle tire? They'll say, pi r squared. Pi r squared. Can you visualize pi r squared? When I hear pi r squared, I can visualize an equation, pi r squared, right? But I can't visualize a thing. I can't even visualize a circle. The equation to me is good for calculations, good for measurements, but you're not going to tell me what it is. I have no visualization for what it is just from pi r squared. Now the bicycle tire is a simple example, but most everything else, it gets more complex. When they're talking about motions, talking about planets orbiting, talking about friction, talking about any type of movement, motions, trains, cars, like I said, planetary orbits, anything, they're going to use these complex equations to describe what it is. And I can't see it. There's nothing there. I can't visualize it. Right? Give me the bicycle tire with materials, what's it made of, what's it look like, the colors, textures. That works for me. The equations don't tell me anything. Right? But the vast majority of scientists look at this. Now let's talk about some of the famous scientists who look at these in different ways. Like I said, 99% of physicists prefer the mathematical view. Newton was probably the first. As a matter of fact, I read his book, Principia, and several times in his book, he said, I do not care what things are made of. I only care that I can calculate them and quantify them. Which is good. I mean, that was his skill, that was his strength. That's good. But that's where his interest was. Einstein was another. I've read a lot of Einstein's works, a lot of his papers and a lot of his books. And several times he's talked about the goal of physics is to get something into a mathematical equation. That's very important. He never said the goal of physics was to understand how things work, or how things operate, or what things are made of. Not once has he ever said that. But on several occasions, he said that the goal of physics is to be able to understand the universe in terms of mathematical equations. That's the way he thought. Feynman. I read a book by Feynman, and he has a whole chapter on this. And he even goes so far as to say the universe cannot be described in physical form. According to him, we cannot describe a bicycle tire. We cannot describe a chair. All we can do is make a mathematical equation. And that mathematical equation is a chair, is a bicycle tire. He can't even conceive of the idea that there's a physical form. He says mathematics is the only way to describe anything. Again, these famous scientists, that's how they view the world. And then all the other scientists that most of us have never heard of, who they publish their papers, they get in journals, they have their PhDs, they're all going through this mathematically. And again, I think that's the wrong way to go, because you're not getting the physical structure of what it is. Now let's go geometrical. Geometrical is better because at least you can look at motions and you can look at entities. Okay, you can say, okay, a planet is basically a sphere. An orbit is basically an ellipse. You can track things, you can look at objects, shapes, you can look at motions, and you're going to get a geometrical process out of it. One of the most famous to do this was Kepler. Kepler thought entirely in geometry. As a matter of fact, he spent a lot of his time teaching geometry back in the day. Now, he was the guy that came up with his 3 laws of planetary motion. And if you notice them, they're all geometrical. They're all geometrical laws. He also changed the orbit from a circle into an ellipse. Again, because he could think geometrically. Okay. Also, not known to many people is that he was one of the first to look at the crystalline structures of rocks and gems. He was one of the first to study crystallography, basically, in his own way. And he could do this because he thought geometrically. Geometries came clear to him. They were just intuition to him to look at things in geometrical fashion. And so he studied many of the rocks, many of the gems, and he started his own ideas of how to categorize things in a geometric way. And I like that. I think that helps a lot to look at the geometry in a particular way. Einstein was another. He was very much mathematical, but also very much geometry. He loves the idea of space-time and of the curved universe. Space-time, really that's just a form of geometry. Space-time is like saying length-width, right? Same sort of thing. Space-time, length-width. That's geometry. Relationships. Curved space. Curved is a geometry. Now, he wasn't the first person to come up with the idea of curved space, but he loved the way of geometrically looking at things, right? And so he used it. So I'd say those are the two main, most famous geometrical physicists. Now, since then, there have been a lot of people. If you read scientific papers like I have, there is a whole category of physicists who talk about the universe in terms of geometrical structures, geometrical shapes. Okay? So it's one way of looking at it. Mathematics is the most popular, I think the least effective. Geometrical is, I would say, about 5% of the scientists, the physicists, and actually does have some use. I still don't think it's quite accurate because it doesn't tell you what things are made of. It doesn't tell you how they work, but it has its use. Okay? Then we get to the physical. What is the object made of? What causes the object to move? Why does the object do what it does? What are the mechanisms? What are the processes? What's it composed of? That's how I look at the universe. That's how I look at every science puzzle, is look at what it is. And I think that's the best and only way to look at things. Really, when you finally get down to it, it's the ultimate way to go. There have been several great scientists who've been able to see things in a physical way and make great insights. Newton had a little bit of that in him, definitely, through some of his experiments and some of his conclusions. He had a lot of that in him. Faraday, who came up with the idea of energy fields, he was a physical thinker. He was also a great experimentalist. But the idea of the fields, again, he's thinking of a physical entity, physical processes of how all these energies will work. Einstein did one good thing, maybe two, as physical. He came up with the idea of the photon, which really actually kind of goes back to Newton's corpuscular theory of light. But, he revamped it to photons and the photoelectric effect. That is a physical explanation. Light exists in photons, and when you apply enough energy, the photon will be released. That's a physical phenomenon, a physical explanation. And to me, that is the most important thing that Einstein gave us. Not relativity, but the photon and photoelectric effect explained. Einstein also was good at the physical when he came up with talking about Brownian motion and the processes being caused by atoms and molecules moving around. That's a physical explanation, a physical process. Boom. Now, I wish Einstein would have stayed with that, because after he published those few papers, he left physical world altogether and went straight into geometry and equations. And he never came back to the physical world again, which I think shows a lot of errors. There are a lot of errors in Einstein's thinking, a lot of errors in Einstein's papers. And those can be traced because he's looking at things not as a physical form, but geometric and purely mathematic. Then to go physical, we have to jump then to Niels Bohr. Niels Bohr was very much into physical. He wanted to know why things were the way they were. He studied the atom in great detail. He basically took all the information, all the experiments that were done. He looked at the atom and he peeled it off layer by layer. He built it up with his electron orbits and the electron leaps, quantum jumps. That was all his brilliance. because he was looking at it physically. He was always imagining, if I had the powerful microscope to actually look inside the atom, what physically would it look like? What are the physical entities involved? How do the physical processes work? He thought very physically. I think that was marvelous. Heisenberg, too. He also thought physically. He wanted to know what was going on inside. He was a great mathematician. Yes, he was. He was superb at logic, which I also love him for that. And he also thought physically. Okay? And even though he was good at mathematics, it really is not the mathematics, I think, that was important. Now, he came up with the first form of quantum mechanics as a mathematical formula. And I think it's superb. I even think it's better than Schrodinger's. So he's a whiz, definitely, at mathematics. But in terms of understanding what is, he goes for the physical. Okay? All right. So we have Faraday, we have some of Einstein, Bohr in a big way, and then Heisenberg. Physical, he knew physical and mathematical. Then we proceed. That was the last of the physical. Everyone else thinks mathematical, 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 mathematical. Everything's mathematical. Everything's mathematical. Even some of the most ridiculous theories that are proposed, they're all mathematical. Stupid ideas. I mean, people proving and disproving things because mathematical theories is basically saying, there can't be any more solutions because my mathematical equation says there can't be any more solutions. There can't be any more, we can't have any many missing variables because my equation says there aren't any missing variables. Maybe your equation is actually missing variables and therefore you're missing variables. It's complicated. Anyway, so it gets complicated, it gets wrong, and then it's philosophical and it's just ridiculous. All right? So, the next person we get to is Stephen Hawking. Now, Stephen Hawking also thinks physical. One of his books that I like, I read in the very first page, he talks about that. He says, mathematics is good, but I can't visualize mathematics. It's much easier if I have a picture in my mind. When I read that, I said, yes, finally again, someone who thinks like I do. A picture in my mind. And ultimately, that's the way to go. Now, me, yes, I've gone through my higher education and I've done all the calculus stuff. Yes, I've done a lot of computations myself. With all my nuclear power books, I went through all those calculations myself. I've double-checked a lot of people and their ideas, some proven right, some proven wrong through the mathematics. I've done that myself. But mathematics doesn't tell me a whole lot of how things work. And that's why I never use math. I don't use math in my books. I don't use math in my presentations. Because mathematics is able to measure, is able to predict, it's able to compute. But it's not able to tell you what it is. I'm after the bicycle tire. I want to tell you what it's made of. I want to tell how it works. I want to, you can hold it in your hand, what it looks like. You can feel it, you can touch it, you can visualize it. It's all right there. And that's why I don't use math. If I have to use math to give some examples of comparisons, then it's always going to be simple math. Simple numbers. Simple equations. But even that is only as needed. Right? I do concepts, physical form, physical entities. Okay? So there you have it. Those are the three ways that physicists tend to look at anything in the universe. Physical, geometrical, mathematical. Most look at it mathematical, 99%, but it really doesn't tell you anything. And I think pretty much we should ignore it. In fact, a lot of those mathematics are flawed, which will be another topic. Geometrical, at least it gives you a shape. It tells you the motions. They've examined things, they've tracked things. At least that gives you something to look at, to study. But again, ultimately, you want to know the main thing, which is why. What is it actually made of? Why does it actually do the thing it does? The mathematics can tell you the relationships. The geometry can really help you see the patterns. But ultimately, you're going for the physical, the why. And Faraday, Bohr, Heisenberg, Hawking, and myself are only about, I would say, half, 0.5% of the population and scientists who think that way. And I think you'll agree. Thank you.